Greetings, Chem 2 students. Mr. Keister here with you again today. This is the video for Tuesday, November 24th, 2020, which is our scheduled 67th day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do-nows and see what the schedule is for today. So today we're going to pick up a new assignment, the mole and molar mass, page 89. We started Unit 6.1 yesterday and looked at Avogadro's number. That assignment I am not going to collect because there are some more problems regarding that on this assignment. I'm going to look at that again today as well as move on. And so I decided not to collect the Avogadro's number assignment. So, but make sure you know how to do it though. Of course, I got the answer key posted in the back on the board if you're at school. I also have that posted on the answer keys page in Canvas if you or we are at home. So make sure you double check your work. Make sure that you showed everything you were supposed to show. That, of course, is very important, especially in this unit. A lot of math in this unit. So also, this is a big one. Your second homework for today, which was from last Friday, was to complete the Unit 5 review assignment over organic chemistry. That is due now. So you should have that on my desk if you're here in school. If you are at home, you need to submit that to me electronically via Canvas, okay? Again, no answer key posted on that one, so it's worth quite a few more points than what a normal review would be. And again, even though we didn't have a test over Unit 5, which was a mini unit, that information is going to show up not only on this test, but the next one as well, and also on the final. So we're going to continue on today with Unit 6.1 on the mole. Today we're going to learn how to deal with moles and mass, which involves the use of a term called molar mass. So you'll have a homework assignment over this that is due tomorrow. And again, always show work, label when doing any type of computational problems. Make sure you round correctly as well. We talked about that yesterday in regards to the mole. So let's pull up the notes and let's get going. Going to need your periodic table today. All right, so previously we learned, this is way back when, that the average atomic mass or average mass number of an element is equal to the average number of protons and neutrons combined that it has in its nucleus. We also learned that the mass of the protons and neutrons, and hence the nucleus, is virtually all of the mass of the entire atom. Remember, the electrons have very little mass as compared to the proton or neutron. If you remember, an AMU was equal to approximately 1.67 times 10 to the minus 24 grams. That's one AMU, all right? We can now use that number to quantify a mole in terms of mass in grams, and this is now called molar mass. The mass in grams of 1 mole of any particular chemical substance. It is measured and labeled in grams per mole. And again, if you want to abbreviate mole by dropping that E off, of course you can do that. So grams per MOL, all right, grams per mole. Now, so interesting fact that we can now use this average atomic mass in terms of grams per mole. Well, think about it. You know, an AMU is either the mass of a proton or a neutron, all right? So if we have 1 mole of AMUs, we have 6.02 times 10 to the 23rd of those atomic mass units, or 1.67 times 10 to the minus 24th grams for each one of those AMUs. So when you take the mass of that 1 AMU in grams and you multiply it by Avogadro's number, you have the mass of 1 mole of 1 AMU, all right? And then, of course, so for carbon, which has an average atomic mass of 12, because it has 6 protons and 6 neutrons, its average atom does anyway. So you take that 1 AMU and multiply it by 12, and then multiply it by Avogadro's number, you now have a term, a number that is the mass of 1 mole of that particular substance. And of course, if you do the math there, you come out with no surprise, 12.01. All right. So that not only is the average atomic mass in terms of AMUs for carbon, it is also the molar mass of carbon, which is the mass of 1 mole of carbon atoms. All right. And so it is also 12.01 grams per mole. Now, we can then use molar mass to do some conversions. Now, let's talk about molar mass first. Now, normally, molar mass or average atomic mass, which is where we get molar mass, we've talked about this before, a lot of them are rounded to 2 decimal places. Some are whole numbers, some are 3 decimal places, kind of all over the place. What we're going to do in this class, what I've seen many times before, is we're going to round that average atomic mass in terms of molar mass to the whole number. Now, when you get to mastering or whatever, they may require you that you leave it at 2 decimals or whatever, and that's fine. But for our purposes, we're going to round molar mass to the whole number. All right, so just make a note of that, please. So for a monatomic element, the molar mass of a monatomic element is simply numerically the same as its average atomic mass. So like we said for carbon, which is 12.01, we would round that as a whole number to 12 grams per mole. 12, all right. So for copper, which is 63.55, we round that to the whole number. That would be 64 grams per mole. In other words, there are 64 grams of copper in 1 mole. There are 12 grams of copper, or of carbon, excuse me, in 1 mole. All right. For barium, 137.3, that would be 137 grams per mole. All right. So if it's a monatomic element, the molar mass and the average atomic mass are one and the same. All right. Same. All right. Let's advance the screen here. So for diatomic elements, take its average atomic mass times 2. So for nitrogen gas, which is N2, there are 2 atoms of nitrogen in there. All right. You take its average atomic mass, which is 14.01, round that to the whole number, 14, and multiply it by 2. Then the molar mass of N2 would be 28 grams per mole. All right. For oxygen, it would be 16. Oxygen is 15.99, 16.00, depending on what periodic table you got. But either way, that rounds to a whole number of 16, and since there are 2 of them, 16 times 2 would be 32 grams per mole. All right. Now, I'm going to put a little star by chlorine, Cl2. All right. So chlorine. All right. So chlorine's average atomic mass is 35.45 AMU. All right. So if we're dealing with only 1 chlorine, such as in a compound that has 1 chlorine, if we round that 35.45 to the whole number, we're going to use 35. All right. So if only 1, we're going to use 35. All right. 35. If we have 2 or more, and we're going to take 35.45 times whatever that number is, and then round to the whole number. So for instance, in a molecule of chlorine gas, which is Cl2, it would be 35.45 times 2, which is 70.90. That rounds to 71. All right. So in other words, it's not 70 for Cl2. Even though we're going to use 35 for 1 Cl, if we have a Cl in a compound or whatever. But since we have 2 here or more, and that would be the same rule, we're going to take 35.45 times how many we have and then round that to the whole number. So Cl2 then would be 71 grams per mole, not 70. All right, remember that. Okay. If you don't, that's going to throw your calculations off a little bit. All right, so on the next page, for a molecular ionic compound, we're going to take the average atomic mass of each element multiplied by the subscript, which tells you how many of that particular atom or ion is in the compound, and then add them all together. So for NaBr, all right, so Na rounded to the whole number is 23, and Br rounded to the whole number is 80, and if we add those two together, we get 103 grams per mole, which is sodium bromide's molar mass. Potassium sulfate, K2SO4. So we have two Ks. Each K is 39. That'd be 78. One sulfur, 32. And oxygen, as we said earlier, is 16. You're going to remember a lot of these very quickly. 16 times 4 is 64. And if you add those three numbers together, you get 174 grams per mole. So CaCO3, calcium carbonate. Calcium's 40. Carbon's 12. And 3 oxygen, 16 times 3, 48. 48, 60, that'd be 100 grams per mole for CaCO3. Sodium phosphate, Na3PO4. Okay, so Na is 23. 3 of those would be 69. 1 P, 31. And 4 O's would be 16 times 4, 64. And that would be 164 grams per mole. Potassium acetate, K is 39. 2 carbons, 12 times 2, 24. 3 hydrogens, 1 times 3, 3. 2 oxygens, 2 times 16, 32. So we got 39, 63, 66, and 32, 98 grams per mole. Make sure that when you're finding the molar mass of a compound that you show your work as to how you got that number. All right, make sure you show your work. That's a requirement. Okay? No, we know now that some compounds have parentheses in their formula with a subscript number outside the parentheses. For these compounds, make sure that you distribute or multiply whatever is inside the parentheses by that subscript number. All right. So let's look at some of those. So here we have magnesium hydroxide. So this just has 1 Mg, which is 24. Now, in the parentheses, we have OH. Yeah, but there's a 2 out here. So what that means is there's actually 2 O's and 2 H's. All right, we distribute that 2 to both of those. So 2 O's would be 32, 2 H's would be 2, and we add that up, we get 58 grams per mole. Calcium phosphate, there's 3 calciums. Calcium is 40, so that would be 120. Now, we got a 2 outside the parentheses here. There's a P in there, so it actually means there's 2 P's, all right? P is 31 times 2 is 62. And how many O's we got? There's a 4 inside, but there's a 2 outside. All right, that's not 6 O's. How many O's is that? It's 8. All right, remember you distribute that 2, you multiply. So there are 8 O's in there, and 8 times 16 is 128. Don't make that mistake. I see that a lot. All right, there are not 6 O's in that. There are 8. Okay, so let's see. 128 and 62 is 190 and 120. 310. Yes, 310. Aluminum sulfate. All right, so there's 2 aluminums, which would be 27 times 2, 54. 1 S, but there's a 3 out there, so there's actually 3 S's. S is 32, so that'd be 96. And now we have 4 times 3, 12 O's, right? It's not 7. It's not 4 plus 3. It's 4 times 3, 12 O's. All right, and so let's see, 12 times 16, 192, I believe. Boy, it helps to know the times tables. When did I learn those? I don't know, 3rd or 4th grade, I think. Still comes in handy. All right, so let's see, 54, 96, 150, 342 grams per mole for aluminum sulfate. Are you remembering the names of these compounds? You need to, all right, you need to. Nomenclature, got to know it. Barium, 137. This barium nitrate, so we have NO3 parentheses 2, so there's 2 N's in there. 2 times 14, 28. 3 O's times 2 is 6. 9 times 16 is 96. 65, 261 grams per mole. And the last one, ammonium dichromate. Remember that name? Dichromate, ammonium dichromate. With NH4, 2, so we have 2 N's, 28. We have 4 times 2, 8 H's, which is 8. We have 2 chromium. Gotta look that one up. Chromium is 52 times 2, 104. And 7 O's, 7 times 16, 112. Let's see, 36, 140, 252 grams per mole. All right, so you see how to determine molar mass there? All right, we're using average atomic mass, rounded to the nearest whole number. Add them up. All right, add them up. Show your work. So now we can use molar mass as a conversion factor in dimensional analysis for proportional reasoning to solve conversions involving mass and moles. So again, mass and moles. So 1 mole, all right, 1 mole is equivalent to this mass that we've just determined here in grams. All right, remember that. So in our first example here, what mass in grams? So we're looking for mass of carbon dioxide would be found in 4.70 moles. All right, so we're going to start with what we're given here, which is 4.70 moles of carbon dioxide, CO2. Again, got to know your nomenclature, got to know your formula. Now we want to convert that to grams, so we're going to need molar mass for that. So we need to determine the molar mass of CO2. So C is 12, and O2 would be 16 times 2, 32, 44 grams per mole. Make sure you show that, all right? Because we're using that here, so the 1 mole's got to go down below 44 grams CO2 up top, all right? So there are 44 grams in 1 mole. I need to see where that 44 came from, all right? So make sure you show that, all right? If you don't, you're going to lose points. All right? Show all your work. Multiply. All right, so how do we round? Well, again, molar mass is a constant, just like Avogadro's number, all right? For each substance, it has its own molar mass. Again, the number of sig figs with molar mass can vary greatly, depending on how big it is. And so, again, we're not going to use molar mass to determine sig figs. We're going to use the sig figs of our original measurement, which is 4.70 moles, which is 3 sig figs. So we do that, and we get 207 grams of CO2. Again, don't use molar mass to determine sig figs, right? Because it is a constant. Okay. All right. Next page. How many moles of silver nitrate are found in a sample with a mass of 67.25 grams? All right. So if we start with 67.25 grams over 1, silver nitrate. Okay, we need to know the formula for that. So silver is a transition metal, but remember it's always a +1 ion. All right, so Ag +1. Nitrate is NO3 -1. So they're going to combine 1 to 1. So the formula is AgNO3. Right? This would be 67.25 grams of AgNO3. Make sure you include that in the label. Times. You want to convert it to moles. All right, well, the gram's going to have to go down here. So they cancel, and the mole's up top. And remember, the molar mass is how many grams there are in 1 mole. It's always 1 mole. All right? So how many grams is that? Well, silver is 108, rounded to the whole number. Nitrogen 14, 3 O's is 48, 170. 170 grams per mole. So the 170 goes right there. All right. And so now we're going to divide. The grams cancel, And our original measurement has 4 sig figs, so our answer needs to have 4 sig figs now. 0.3956 moles of AgNO3. 4 sig figs there. Remember, we had 3 up here. All right. Okay. Next one. A sample of magnesium phosphate has a mass of 42.5 grams. How many moles do we have of that? Okay, well, magnesium phosphate. All right, so magnesium, 2A, plus 2. Phosphate, PO4 minus 3. So the formula for magnesium phosphate then would be Mg3 PO4 parentheses 2. See how important nomenclature is here? We're going to calculate a molar mass. We got to make sure the formula is correct in order to do that. If you can't write a formula, then the rest of this goes haywire. All right? So you got to know your nomenclature. Let's just go ahead and figure that molar mass real quick. So Mg is 24 times 3 is 72. PO4 is in parentheses 2, so we have 2 P's, which would be 62, and 8 O's, 4 times 2, 8 O's times 16, 128. 262 grams per mole. See how crucial knowing that number is? All right? Can't know that number without a correct formula. All right? So 262. So we have 42.5 grams of Mg3 PO4 parentheses 2 over 1. There are 262 grams in a mole. So the gram's going to have to go down below. 262 grams of Mg3 PO4 2. 1 mole up top, Mg3 PO4 2. The grams cancel. Our original measurement has 3 sig figs, so our answer needs to have 3 sig figs as well. 0.162 moles of Mg3 PO4 2. 3 sig figs. Again, make sure you are showing all the work that we talked about here. Make sure you are labeling your conversion factors, showing how they cancel out and so forth. And make sure you are rounding correctly, okay? A lot involved with these, all right? The least of which is certainly not nomenclature. You've got to know how to write a formula. Can't stress it enough. All right, so let's move along here and finish up this. So what we're going to do now is going to incorporate what we learned yesterday with number of particles, or Avogadro's number, with mass, all right? So let's do a quick review here. So we know now that 1 mole. So 1 mole is equivalent to 6.02 times 10 to the 23rd representative particles, which could be atoms, molecules, or formula units, depending on what type of substance it is. We also know now that 1 mole is equivalent to a mass in grams, equivalent to the substance's molar mass. All right? So we can go 2 directions now with a mole, and that's what we're going to do right here. I'm going to show you that we can go 2 different directions with this. So, a sample of nitrogen gas. Okay, nitrogen gas is N2, all right? N2. It's diatomic element. Contains 1.75 moles. What mass of nitrogen gas is contained in this sample? So we're talking about mass. So we're going to use molar mass. We're going to use Avogadro's number if we're talking about mass. Or obviously we're going to talk about molar mass. All right? Mass, molar mass. Okay? So the molar mass of N2 is 28 grams per mole, 14 times 2. So we're going to start with our 1.75 moles of N2, put it over 1, And now we're going to convert that to grams using molar mass. So in 1 mole of N2, which we go down below so they cancel, we have 28 grams of N2. And to 3 sig figs, 49.0 grams of N2. All right. Now, part B. What quantity of molecules are contained in this same sample? Well, we have the same quantity, 1.75 moles. Start with that again. But now we want to go to molecules. What's the relationship between a mole and molecules? A molecule is a representative particle. All right. The relationship between moles and particles is Avogadro's number. All right. So the 1 mole is still going to go down below here. And now it's 6.02 times 10 to the 23rd molecules of N2. And the 3 sig figs here, we have 1.05 times 10 to the 24th molecules of N2. All right? Again, the 3 sig figs based on our original measurement. Okay, so now, so what does this mean? Well, both of these numbers here are equivalent to the same number of moles of N2. Okay, you see the connection? So now what we're saying is, if we have 1.05 times 10 to the 24th molecules of N2, that number of molecules is going to have a mass of 49.0 grams to 3 sig figs, of course. All right? Those two numbers both represent the same quantity of N2, which is 1.75 moles. So we took that 1.75 moles now and went 2 different directions with it. All right? But these 2 quantities describe the same amount of N2, 1.75 moles. One is expressed in particles, in this case molecules. The other is expressed in grams, okay, or mass. So the last problem for today is a combo problem. Sorry, the last 2 problems are combo problems, all right? So we can combine both representative particles and mass into a single dimensional analysis calculation, multiple steps, using the mole. So here we have a sample of water, and it has a mass of 54.75 grams. So we have water. All right. How many molecules are in this sample? All right, how many molecules? We're going to start with 54.75 grams of water. Now, we're trying to find molecules. Well, we need to get to moles first, because the mole is the way we can get to either one of those things. So if we're starting with grams, we're going to have to use water's molar mass to get us to moles. All right. So water is 2 and 16, which is 18 grams per mole. Make sure you show that. So in 1 mole of water, there are 18 grams of water, and the grams cancel. Now we have moles. Can we get to molecules? Yes, we can, using Avogadro's number. So in 1 mole of water, which would now go down here so we can cancel those out, there are 6.02 times 10 to the 23rd molecules of water. And now we have molecules. So 54.7 times, or 0.75 times Avogadro's number divided by 18 and rounded to, let's see, 4 sig figs would be 1.831 times 10 to the 24th molecule of water. So this mass of water is equivalent to this number of molecules of water. All right. How do we know that? Because they both run through the mole. All right. They both run through the mole, like it said right here. Okay. And then the last one, a sample of silicon dioxide contains 8.25 times 10 to the 24th molecules. What's the mass of this sample? All right. Well, we're going to start with molecules. Silicon dioxide, molecular compound, prefixes. All right. Covalent bonding, molecular, prefixes. Silicon, 1. Dioxide, 2. SiO2. All right. So we have 8.25 times 10 to the 24th molecules of SiO2 over 1. We need to convert that to moles first before we deal with mass. So in 1 mole of SiO2, there are how many molecules? Avogadro's number. 6.02 times 10 to the 23rd molecules of SiO2. Those cancel. Now we want grams, so we need molar mass. So silicon, what is silicon? 28. 2 O's would be 16 times 2, 32. 60 grams per mole for SiO2. Make sure you show that. I need to see it. Now the 1 mole goes down here, so the moles cancel, and the 60 grams of SiO2 go up top. So again, we're converting between number of particles and mass by going through the mole, because they both run through the mole. All right. So we'll take 8.25 times 10 to the 24th times 60 divided by Avogadro's number. Original quantity, 3 sig figs. And then we get 822 grams of SiO2. 3 sig figs. All right. So we can use the mole to run to either particles or mass. All right. Either one. We can quantify a substance 2 ways through the mole. All right. Number of particles or mass. So that concludes today's lesson. Quite a bit longer than yesterday's. All right. So today's assignment, you're going to be dealing with molar mass for the most part, but then towards the end, as we did here, we're going to look at the relationship that exists between mass and number of particles, which of course both now run through the mole. So again, show all of your work, label all of your conversion steps, make sure that you cancel out the units, show that, make sure you round correctly, make sure you show all your molar mass work. Okay? So until tomorrow then, this is Mr. Keister signing off. Take care, everyone. Stay safe. Stay focused. Keep working hard, and I will catch you all next time. See you guys.